now the next thing that I want to discuss is a very general result. So, I will not be proving the result today, but I will lay the foundations for that result, and then in our next lecture we will look at a proof of that result, and then we will see applications of that result to show how we can show other lower bounds on circuits which have other, or circuits of formula which have other kind of structures. Okay. So, we have defined, let us look at a couple of definition. So, we defined what we mean by the star size, right. So, this we have already seen. Now, let us look at the definition of leaf size. Okay. So, leaf size is simple. So, the leaf size of any Boolean formula is the number of leaf nodes that are present in that Boolean formula. We actually already use that over here informally, but formally we can give a definition. So, the leaf size of a Boolean formula is the number of leaf nodes in the leaf node occurrences in the Boolean formula. Okay. So, again as I said, in the Boolean formula you can have the same variable which occurs multiple times. So, for each different occurrence of that variable we will count it again. Okay. So, it is the total number of leaf nodes. I am not saying it is the total number of variables, it is the, yeah. So, this is called the leaf size, and then we have the star depth. So, the star depth of a it can be for formula as well as circuit. So, let me define it in terms of circuit. Of a circuit is the maximum number of OR and AND gates in a path from an input gate to the output gate in that circuit. Okay. So, it is the, you take any path from an input to the output gate and count the number of OR and AND gates present. The maximum over all such quantities is the star depth. Okay. And it, well, and well, let me also mention what depth is. So, depth is when you just count the number of gates present in that circuit. Okay. It can be OR, AND and NOT, but when I say star I just mean number of OR and AND. And one more quantity that we would require is what is called the alternation depth of the circuit. Yeah. The alternation depth of a circuit is the maximum number of times a path alternates between and or gates in that circuit. Okay. So, now take any path. I can have along that path, let us say I can have the gates as or and or. So, the number of gates present is 5, but the number of alternations is only 2, okay, because you go from or to and then from and to or. Okay. So, that is what we mean by alternation depth. Okay. So, one quick result about the leaf size, something that we already saw. In any circuit or not circuit, any formula, okay, for a Boolean formula phi, leaf size of phi is equal to star size of phi plus 1. So, all we are saying is that you take a Boolean formula. Okay. Now, when I say leaf size, it means the total number of leaf nodes in that formula, and star size is the number of internal nodes in that formula, and we are looking at we are not counting the NOT gates over here. Now, even if this Boolean formula contains AND, OR and NOT gates, if you look at a NOT gate, what is the fan in and fan out of a NOT gate? Both are 1, right. So, if you look at a Boolean formula, okay, then the number of internal nodes which have degree 2 is 1 less than the number of leaf nodes. Okay. So, this actually directly follows from the theory of binary trees. So, what else do I need? Yeah. So, one more quantity is related to Hamming distance. So, let okay, take two strings. So, let sigma and tau be two strings of length n, okay, such that sigma is not equal to tau and the Hamming distance of sigma and tau is equal to 1. Okay. So, two strings which differ at exactly one position. Okay. Now, for two sets over 0 1 star, so then we call them something, right? Okay. Then we call sigma and tau as neighbors. If for two strings the Hamming distance is equal to 1, we call them as neighbors. Now, let us take two sets. Okay. So, let A and B be two subsets of 0 1 to the power n. Okay. We define NAB to be the size of the set of tuples sigma tau such that sigma and tau are neighbors. So, what are we counting over here? So, take two sets A and B, and in A and B I am counting that if I take so A and B are neighbors, and so A, yeah, so sigma is in A and tau is in B. Okay, sigma and tau are neighbors, and sigma is in A and tau is in huh? Exactly. So, if I look at sigma comma tau as belonging to A cross B, then what you are saying is correct. Yeah. So, if I take two sets A and B, okay, how many tuples are there such that one element is in A and the other element is in B, such that they are neighbors. So, that is NAB. So, now we are in a position to state the theorem. So, this theorem was by Khrapchenko. So, it is called Khrapchenko's theorem. I am sorry.
A can be any sets. They need not
A can A and B can be anything. They need not be disjoint. They can have common elements. Yeah. Here, in this definition, they can be anything. But when we prove Khrapchenko's theorem, we will consider A and B to be disjoint. So, let f from 0 1 to the power n to 0 1 be a Boolean function, and let A be some subset of f inverse 0 and B be some subset of f inverse 1, then what Khrapchenko proved is that L star over and or and not of f is greater than or equal to n a b square divided by cardinality of A times cardinality of P minus 1. So, let us try to understand this. So, what this is saying is that if I look at a Boolean formula, okay, and if I look at, let us say, two sets A and B such that A gets entirely mapped to 0 and B gets entirely mapped to 1, A and B can be anything, it is basically a subset of these two quantities. Then the number of pairs, so basically if there are lot of pairs from between A and B which are neighbors, then the complexity of f goes higher. Okay. And if A and B are in some sense very separate, okay, there are not many neighbors between them, then the complexity of f becomes smaller. Okay. So, this is like a very nice connection. Okay. It kind of relates the circuit complexity, or in this case the formula complexity of a function with how many tuples are there which are close or not so close. Okay. It is the so f inverse 0. So, f maps strings to 0 and 1, right. So, f inverse 0 is all those strings which get mapped to 0. F inverse 1 is all strings which get mapped to 1. Because yes, it is not equal, it is subset. It can be any subset. Yes. For all subsets this is true. So that is why it is a much stronger result. It is not just for f inverse 0, f inverse 1, but any subset. Okay. And we have this minus 1 because ultimately what we will prove is that we will prove that for the leaf size. So, basically we will prove that the leaf size of a tree is greater than this. So, if I take a binary tree, okay, then the number of leaf nodes is greater than this quantity, which means that the number of internal nodes is greater than this quantity minus 1. So, that is the reason we have this minus 1. Okay. So, we will see this on Friday. So, f inverse is all strings which map to 0, f inverse 0. Okay. So, it is a standard, I mean you should look at the definition of functions. So, this is like a standard notation for functions.
And here in this case A and B will be disjoint.
Of course, because two strings cannot, I mean a single string cannot go to both 0 and 1. By definition they are disjoint. Okay. Okay.
Sir, if there are many neighbors, then this value of L star will get higher.
So, then the bound on L star is higher.
By many, you mean ki the minimum of the cardinality of A and B?
No. By many I mean just if this quantity is large, then this is also large, that is all that I mean.
Can you set a bound on N A B? Minimum of A and B less than the minimum of A and B?
I mean you can set a bound, I mean I do not understand you. So, NAB is basically the number of pairs,
Yeah, number of elements of A or B.
yeah, number of elements from A cross B which are neighbors, right.
Yes, can you maximum, that can take a maximum value of
It can take a maximum value of A times B,
A times B?
yeah.
Yeah, minimum of A or B. A to B you are mapping now. So either you can map all the elements of A to some element of B.
See, if all the, I mean it can be, so I am saying that the upper bound on this will be I take all elements of A times all elements of B, let us say all of them are neighbors, that is all, that is what I am saying. That is a trivial upper bound.
It can have two neighbors also.
It can have more than one neighbor, yeah, and many neighbors. Okay. Okay, so thank you.